All right. Well, thank you everybody for coming today for the latest talk in the MERL Seminar Series. And today's speaker is Samuel Clarke. He's a sixth-year PhD candidate in computer science at Stanford, advised by Professor Zhejian Wu, who was a previous speaker in our seminar series. His research interests are broadly in the field of embodied perception, so far focusing on acoustic perception for learning from physical sounds in real environments. Um, Before Stanford, he completed an MS in robotics at Carnegie Mellon. And before that, BS degrees in mechanical engineering and computer science at Georgia Tech. He's currently supported by a Meta Fellowship and previously received an Astronaut Foundation scholarship. And I think he's written some really nice papers about using audio sensing for robotics. And so we're really excited to have him here. And with that, thank you, Samuel, and take it away.
Great. Thank you, Gordon. As he said, I'll be talking about how we approached sound from a robotics perspectives and the principles that have guided our work to make robots more aware of their environments through sound. So I'll be talking about audio for object and spatial awareness. So I'm going to start by motivating this talk with a few videos that you might have seen on social media before. At least initially, they should be pretty familiar, but you may notice a little bit of divergence from familiarity as they get a little further. But first of all, we're going to see this video of a really popular humanoid robot, the Tesla Optimus robot, placing battery cells into a tray. You'll notice that there's a battery that has been improperly placed, and the robot is able to see this and recover from the failure as I start the video here. So in this case, the failure was quite obvious from using only vision, but you could imagine how the sound of the battery cell landing in the case might also have informed the robot that there was a failure, as it would expect a characteristic thud sound when the cell landed successfully in the bottom of the case. Yeah, vision was sufficient there, but audio also could have augmented that. Now we'll see a case where vision is not sufficient. Um, Here, the robot is manipulating eggs, and if we listen carefully, hopefully we'll hear what goes wrong here. And as I said, this may initially seem familiar, but if you pay attention, you'll notice a little bit of divergence from what you may have seen on social media. Okay, so there we heard that the robot cracked the egg while it was changing hands from one to the other. And whereas that may not have been apparent from vision or even tactile sensing, that was quite obvious from sound. Here we'll see another video where sound is quite informative for this robot. Again, it's putting these battery cells in a case, and an anomaly occurs, and that's quite evident through sound. Okay, there, it sounded like something must have dropped, but the robot was only attending to the battery cells it was putting in the case. So it didn't necessarily see what happened, but it was able to hear that something dropped. In this case, however, we did have a camera on the robot's foot to show exactly what happened. So yes, it indeed had dropped a battery cell. So these examples are kind of tongue in cheek, but I think they show two important things. We were able to detect, hopefully, you were able to detect that I had shoddily doctored those videos with sound for two reasons. One, in the example of this battery hitting the ground, that's just a AAA battery, whereas one would expect those large battery cells the robot was manipulating to sound have much lower frequency, fundamental frequencies. And also the environment of the recording, the way the sound of the battery reverberated through the room sounded much different than one would expect from that large factory environment that the robot was actually working in, which I think demonstrates both our humans' intuitive understanding of both the object acoustics as well as the room acoustics in inferring and diagnosing these anomalies. So that being said, we've had two main thrusts of audio learning so far in our work here. First of all, we've done a lot of work in object acoustics, for example, our diff impact paper and our real impact paper. And then more recently, we also have on the room acoustics side, the Hearing Anything Anywhere paper, as well as the SoundCam paper. There's a few themes of the following works that would are kind of motifs that we see through that we've arrived at through doing these different works. One is that they tend to be audio focused. I would say vision is very important, but we try to abstract out the orthogonal vision challenges and focus only on the audio challenges. So there are cases where definitely vision would have augmented awareness and from what we got from audio, but we wanted to focus specifically on what we could get from audio. We also try to use physics-based models and physics-based model biases in each of our projects. These physics-based models are often differentiable, and because of that model bias, they're very sample efficient, and they often give us interpretable parameters which we can transfer to other tasks. We also have been powered by taking high fidelity data sets on a budget. We take these data sets from controlled and in the wild environments. We make very intentional hardware choices down to the model of the microphone we're using. And we try to collect more than enough data and more annotations than we even plan to use so we can essentially kind of future-proof our data sets. It's very important for us that our algorithms work on actual real data, which actually, unfortunately, is not as common as one might think in a lot of audio works. Sometimes simulated data is all that algorithms are shown to work on. So I'll start by talking about the diff impact project or differentiable rendering and identification of impact sounds. So impact sounds are ubiquitous in our everyday environments. And here we'll watch a video that shows something we can infer from objects' impact sounds. And this video isn't as tongue-in-cheek, but it does have an interesting wrinkle to it, which you might be able to predict. So there we can see in this video that these glasses, there's no apparent difference between the glasses, and there's no easily apparent difference between the forks, but one of the glasses is in fact plastic rather than glass, and one of the forks is metal, whereas the other one is plastic. And that is not necessarily visually apparent, right? But it's quite apparent from sound when we hear these objects strike each other. So we essentially I'll show this approach of how this rough approach of how we characterize an example impact sound. In this case, striking a ceramic mug with an impact hammer. So here's the initial impact sound in the spectrogram. And I'll show how we decompose this impact sound. So first of all, we consider the impact sound to be a product of the impact force time series acting on the object, as well as the intrinsic impulse response of the object. These two aspects are convolved together to essentially produce a synthesized waveform. And then we have a predicted spectrogram. Each of these three models is parametric and differentiable. And by predicting, by predicting the spectrogram and performing an analysis by synthesis process and comparing it to the ground truth spectrogram by a loss function, we can go back and adjust our estimates of the parameters of each of these different models and as we approach the ground truth spectrogram with our predicted spectrogram. So there, by this analysis by synthesis process, essentially the estimate of the impact forces and the impulse response falls out of this analysis by synthesis process. In reality, it's our model's slightly more complex than this, which will come into play later. We also have a differentiable background noise model, which gets added to these sounds, as well as a room response, which gets convolved with all three of those modules to produce the resulting waveform. An interesting, as I said, like these impact forces and impulse response fall out of this analysis by synthesis process. Here we see the implications of this. On the left, we have the audio of striking that mug. And along the way of collecting the audio, we also measured the impact forces as measured by the force transducer in the impact hammer, which are shown in the graph on the top left here. By estimating those impact forces through the analysis by synthesis process, we arrive at an estimate of the impact forces, which is very close to reality. However, this impact forces were never used as a supervision here. These were just measured for later comparison. Note that there is no sense of scale here. These are all just proportional quantities, so they aren't necessarily calibrated, but theoretically they could be calibrated, and we would essentially be able to estimate the forces that had acted on the object from just sound. Oh, sorry, I played those both at the same time, but I think you get the idea. So we'll see an example of where this can play out directly in robotics, how we can use these principles. So we'll talk about source separation for robot impacts. So when a robot or a human strikes one object with another, like we might consider the example of the video I played earlier where the human was using each fork to strike each glass, the resulting sound is unfortunately inevitably a result of the sounds of both objects and the sounds they make during the impact. So if this fork is striking the mug, the sound the human hears is the combination of both those things. Now, as humans, we have very good intuition about separating out those sounds. I think hopefully from the video before, you could determine when each fork was striking each glass, roughly what was the contribution of the fork and what was the contribution of each glass. And so we'll see how we can use these differentiable models to do this in a principled way. So first of all, here's a video of the robot striking a mug with a fork. Now, as I said, we make intentional choices about microphones. So the microphone we use to record is sitting right here. It is somewhat directional and already filters out some of the lab noise. But there are still some background noises, especially the motor noises of the robot. So by fitting after performing an analysis by synthesis process across multiple recordings of different objects struck with different tools, we essentially get these estimates of each of those modules I discussed earlier. And so if we turn off the noise module when we synthesize the sound, we can essentially approximate a denoised version of that recording. So here I'll play that. And then we can turn off the noise module and the mug model in order to estimate the separated fork sound. And here is the same for the separated mug sound. So now that we have these separated sounds, we can use these separated sounds for the downstream task of classifying the material of the object using just kind of model-free baselines or non-domain specific baselines, such as NMF and DAP. We don't get nearly as good of results on the separated sounds for classifying these materials. Note that this would be kind of an ill-posed problem for just using the original audio, because as I said, the original audio is the combination of two different materials at once. So it's not really well posed to estimate or to predict material from just the original audio. So this shows a valuable application of this source separation and these differentiable models of audio and impact sounds for robotics. For our next project, I'm just going to talk about this briefly because it's more of a motivation for future work. But we worked on this multisensory object data set for sim to real transfer. We took all of these simulated objects and simulated their visual feedback, audio feedback, and touch feedback. And then we tried to show that we could do interesting tasks in the real world. I mainly focused on the audio side myself, and I was a little disappointed by the sim to real transfer of simulating audio versus the real audio that we were trying to do downstream tasks with. So here's a few learning experiences we got from this project. First of all, the simulated sounds are often very different from reality. There are methods of simulating sounds of rigid objects. And if I took an object like this beaker and had a mesh and material properties of it, and I simulated the sounds using one of these frameworks, if I played those sounds for you, you might not necessarily be able to tell that they weren't real sounds. But once I get the real object and play the sounds of the real object, you'll notice a major difference in the simulated sounds versus the real sounds. So this hampers downstream sim to real audio tasks. And when I dug further into the literature of these audio simulations, they rarely even claim to be realistic because, in my opinion, I think the main reason was that they had no benchmarks or metrics for measuring their realism. They would often report improvements in efficiency or generalization or something, but there was never a claim that this is more realistic than all the simulations you've seen before. So our key takeaway from this was that the community needs a data set, benchmark, and metrics for improving the realism of object audio simulation. So my advisor, Jajun, commissioned the construction of a semi-anechoic chamber, again, on a budget, so that we could collect some high-fidelity data sets for performing these benchmarks. And I'm actually sitting in front of it right now. It's right behind me. And we'll see what the result of what the final product was here. Yeah, as we can see, we covered all the walls in this absorptive foam. The ceiling is also has sound absorbing tiles. The carpet is kind of a standard office carpet. So that leads us to our project Real Impact, which is a data set of impact sounds for fields for real objects. This was the first project we used this semi-anechoic chamber for. So everyday objects each make unique sounds that are a product of their materials and geometry, these intrinsic properties, as well as how they are contacted and where the listener is relative to the object. So again, with this beaker, where I strike it on the object is going to make different sounds, as well as where I am positioned relative to that object. And it's not just a volume thing. There's also frequencies transmit differently in different directions. And we'll see how that plays out in later results. But here, I'm going to play a video of different samples of the sound field of striking this mug on the handle here. So in that case, the mug was struck at the exact same position every time, but you may have noticed slight frequency shifts at different positions in the sound field. So for this project, we took 50 everyday real objects of different materials, including wood, ceramic, glass, iron, plastic, polycarbonate, and steel. We also designed a fixturing mesh to place these objects on. Objects are contact conditions of an object significantly affect its impulse response. So we wanted to have as little contact as possible. And we also wanted to measure the sound field below the object. So it was important that we had an acoustically transparent surface to rest it on. We placed each object on the center of this mesh, which is centered in this semi-anechoic chamber. And then we put this mesh is also in the center of this gantry. We also devised a striking mechanism for striking the objects in a repeatable but silent way, which involved this impact hammer, which again has a force transducer in its tip to measure the contact forces on the object. a motor and an electromagnet. So the motor pulls back the hammer into the electromagnet. The electromagnet activates. The motor releases the tension, and then finally the electromagnet will release the hammer. And I'll play that video here. So the electromagnet is very silent, and this gave us a very repeatable ways of striking the object in the same place every time. And as I said, we positioned the objects in the middle of a gantry, which had a stack of 15 measurement microphones. We moved this gantry to 40 different positions in that kind of swept out hemi cylinders. And so with these 15 microphones and 40 different positions, we get a total of 600 microphone positions per object vertex that we strike. And we repeated this process for striking 5 different vertices per object. Here I'll play an example of a few sounds we recorded at different microphones. Note that the impact hammer had this calibrated force transducer in its tip, and so we could measure the contact forces the hammer was using to excite the object. And then because we had those contact forces and the microphone audio, we could deconvolve the contact forces from the microphone audio to essentially approximate an impulse response. So here I'll play the recordings from each of these different microphones in the stack. You'll notice a little bit of a shift in volume and also some frequency shift as we get nearer and further away from the mug here. So we also, because we deconvolve these hammer force time series, we can essentially, that's going to correct for like minor differences in the hammer strike. We can capture the sound field across all these recordings, which I believe I already played those examples for you at the beginning. But one thing I was surprised to find in this project was actually I was actually surprised to see these nodes and antinodes in the sound field emerge. Here we see this is a ceramic mixing bowl. It's a rather large bowl that is radially symmetric. And from striking the exact same point on the object and measuring the sound field at different at different azimuth angles, we see that there are these nodes and antinodes in the frequency transfer, the acoustic transfer of each of these frequencies. It seems to correlate the spatial frequency of these nodes and antinodes seems to correlate with the audio frequency as well. So, I mean, these are rather large differences. It basically, by moving your head to a certain angle, suddenly you're hearing the certain frequencies tens of decibels much quieter. Note that for most of our data set, we collected these sound fields at a 20-degree azimuth resolution because just in the interest of time, we could only, it was taking a long time to sweep through all of these different angles. But for this bowl, we collected it actually at a 1-degree azimuth resolution. And we can see that, especially at high frequencies, we actually are below the kind of spatial Nyquist frequency at a 20-degree azimuth resolution. So this may motivate some like super resolution, like acoustic super resolution approaches or data-driven models that use some measurements and then are able to interpolate at a higher spatial frequency than the measurements are taken. Also, for each of our objects, we had 3D meshes of the objects and from 3D scans. And we also had the material class of each object. So because we had those things, we had all of the ingredients for running audio simulations to predict what the object should sound like. And here I'll compare our measured sounds and real impact to some of these state-of-the-art simulators. So first of all, real impact is our recording. Then the denoise just uses a learning-based denoiser to remove some of the noise from our recording. This ClinePat simulation here is a simulation which models objects as hexahedral meshes, so they're not quite as faithful to the geometry, but it also models the acoustic transfer, or how the sound moves through the air. Neural sound is similar, but it's a learning-based method that models both the object acoustics and also the acoustic transfer. Now, Object Folder 2.0 does not measure the acoustic transfer, or sorry, does not model the acoustic transfer, but on the other hand, it uses tetrahedral meshes, so it should be much more faithful to the object geometry. It even uses second order tetrahedral meshes, so we would expect the frequencies, at least, to of the structural vibrations to match up more closely with real impact. So here I'll play each of these sounds in sequence. Here's real impact, denoised, ClinePat, neural sound, and Object Folder 2.0. So yeah, as you could hear there, as you can see in the spectrogram and here, not only are these objects not matching like each of the frequencies kind of attenuation, but they're not even aligning on much of any of the frequencies of the different modes of each object. This will become even more apparent for the steel spatula, which has a lot of different frequency modes represented. So what we learned from this project was that, again, simulated sounds were confirmed to be very different from reality. Collecting audio data takes a lot of time and care. There's so many different sources of noise and reverberation, and again, like deconvolving out the effects of the hammer. This was quite, this took a lot of attention to detail. And we also noticed that we need better perceptual metrics for audio. Um, Basically, what we were often using was kind of an L2 loss or an L2 distance on the predicted spectrogram versus the real spectrogram, but that didn't seem to capture kind of differences in audio as effectively as we had hoped. There are a few perceptual metrics out there that are publicly available, and then it seems like a lot of industry research teams have announced new, really great perceptual metrics for audio, but they haven't released their code, unfortunately. So it's a little challenging to come up with a principled perceptual metric for audio by which we can benchmark these different simulations or other tasks in audio. So finally, I'll talk about a more recent project, which so far my work has been talking about some of the object acoustic side, and here we'll talk about the room acoustic side. And this is, we call this hearing anything anywhere. So this project started out with the question of,
Daniel,
yes,
we have a question maybe before you get started on the
yeah,
room
definitely.
acoustics. I think good time to take it. Motre, go ahead.
All right. Yeah, thank you. So yeah, nice work, Samuel, the first one. So, I mean, I was curious that there is some prior work from MIT, I believe, which was exploring, striking different objects to categorize what kind of material it is. But then I think in that work, from what I vaguely recall, they were also factoring in the material of the striking, the striking agent. So in this case, that would be the hammer, right? So if you like the perceived sound also depends on that material as well. And the other thing I believe they factored in was also environment. So like whether you captured indoors versus outdoors, like this same event could be occurring outdoors and it might sound slightly different, right? So do you consider these elements?
Yeah, those are a couple great questions. I mean, you're right. I kind of talked earlier about how this, when you have a fork striking a mug, you're hearing the sound of a fork, but I didn't explain how we filter out the hammer. First of all, the impact hammer is very small. The head of the hammer is small enough such that its modes, the frequencies of its modes are actually outside the realm of human hearing. And the tip of the hammer is kind of a sharpened and hardened steel. So when I guess I don't have any, unfortunately, I don't have any plots to show this, but in our dip impact project, we noticed that the impacts were not, they're not perfect, like Dirac impulses. They have like a width to them. However, the width of that impact is a function of the curvature of, there are different models for modeling the impact. A model that works very well is to model the kind of width of that impulse as a function of the local curvature of the two objects, as well as the hardness of the object. So by using a hammer with a sharpened, hardened steel tip, we essentially got as close to a perfect impulse as possible, especially for the realm of audio frequencies. So yeah, if you have like a softer object that essentially is like a low pass filter on the frequencies, but for the hammer, we neither had the sounds of the hammer polluting our data to a significant degree. There's going to be a little bit of sounds of the like the handle or something, and also the strike was sharp enough that it shouldn't have dampened out the vibrations as very much, but the deconvolution should correct for what little of that may have happened. Finally, to your point about the environment affecting things, we collected everything in this semi-anechoic room such that we figured it was much easier to go back and add reverberations than it is to take them out. So if we wanted to take this data and essentially predict the sound field in a different room or outside, we can convolve these different impact sounds with a room impulse response of a new environment and predict what that would sound like in a different environment. Obviously, the semi-anechoic chamber is not perfect, but within the constraints of a decent budget, we got the reverberation to have as little effect on the data as possible. Does that answer your question?
Thank you. Yep.
Okay,
Thanks.
great.
Can-
Any other questions?
I maybe have one question.
Yeah, sure.
So
Okay.
you know, in your first work, you talked about separating the striker from the object being struck, separating those two components of the sound. Did you ever try using this rig to try to collect ground truth data for this separation process?
Wait, we actually never did. Yeah, I guess with the previous project, I guess I was convinced enough qualitatively, but that would have been an interesting task. I think, unfortunately, I don't know if there was much overlap in the objects we tested. But yeah, that would have been an interesting task to compare those two things.
Yeah. I'm not sure how to exactly design that experiment, but yeah, it could be something interesting.
Yeah. Okay. Any other questions or? Okay. Well, I guess I'll move on with this. As I said, this room acoustics project. So we asked ourselves a question of what would a nerf for audio look like? By the time we even started this project, there were some papers that had already come out quickly after nerf claiming to be a nerf for audio. And I would say, first of all, the one question is, what problem is a nerf trying to solve? And so these nerfs for audio that had come out so far, they took a rather obvious approach that I think is probably the correct approach. A nerf for audio should be basically novel viewpoint acoustic synthesis, or whereas a nerf for vision, you synthesize an image of a novel viewpoint given a few different images of an object or a scene at different positions. What does that object or scene look like from a novel position? Similarly for audio, if you have a few samples of what a sound sounds like from different positions, can you interpolate or extrapolate to a new position and estimate what that sound should sound like. Now, so that's one aspect of this question. What problem is the NERF trying to solve? Now, the next question is, how does the NERF solve it? Well, that's more of a matter of perspective. A lot of the previous works that had come along had essentially taken inspiration from the neural architecture of NERF. So they had a positional encoding, they had an MLP for kind of interpolating in the scene. But we wanted to think a little bit more fundamentally of what was it that NERF was able to do with light, and how can we take those principles and adapt them to sound? So first of all, let's think about what a camera records. So a camera records incoming light, and as this light is incoming, each pixel represents the average of a certain kind of angle of rays of light. So there's angular information to each pixel. Also, light travels, unless we're talking about astronomical scales, light travels so fast that it's almost traveling instantaneously. So that's why we call it a snapshot. However, light is missing a sense of scale. Audio is essentially the complement of that, and what we record is essentially the complement of that. So a microphone records incoming pressure waves from all directions. Even directional microphones essentially record like a weighted, at best, like a weighted average of all of the incoming angles at once. And so there's not really great sense of angle of the incoming sound. However, sound travels orders of magnitude more slowly than light. So we get a time series when we're recording sound, and we can possibly reason about distances based on delays of arrival within these time series. So again, light gives us a snapshot and angle information, whereas audio gives us a time series and perhaps some distance or scale information. So in order to kind of approach this problem, we started by collecting data sets of room impulse responses of real rooms of different acoustic properties. Here we have the hallway, which is very reverberant, a classroom, which is a little more normal. We also had our dampened room. And also we wanted to show that our whatever model we came up with could work in more complex geometry. We collected hundreds of microphone positions, but we wanted to show that our algorithm could work in much lower data regimes. So we restricted ourselves to 12 microphones per room, which we considered to be maybe realistic for a kind of a human to put 12 microphones or a single microphone in 12 different positions, where it's not really realistic to collect hundreds of microphone positions in a room in a timely fashion. And we measured room impulse responses at each of these positions in the room. So let's look at one of these rooms, the classroom, and we'll think about how sound travels through the room. In our algorithm, we modeled the specular reflection paths. So we'll see how these specular reflection paths play out. Sound is traveling from this speaker, which is our sound source, to this receiver, which is our microphone. Along the way, sound is going to emanate from the speaker in different directions. And we essentially have kind of these rays of sound that travel in different directions from the speaker and strike these different planes in different sequences. And then by the time they arrive to the microphone, they have struck a different, like a unique sequence of planes, and they've also traveled a total distance, which is going to be proportional to the delay of arrival at which they arrive to the microphone in the impulse response. So here we'll see how these different rays, each represented by a dot, travels. So each ray is striking each wall, and each wall essentially is a frequency filter on that sound. And then over time, these different rays, depending on the angle and the sequence at which they emanate from the speaker, start to arrive at the microphone at different times, and then they show up in this impulse response at different times. Note that along the distance, they also attenuate in volume. So the later a ray arrives, the less loud it is in its contribution to the impulse response. So this shows kind of our specular reflection path tracing model in play. Basically, we decomposed each room into the salient planes of the room. Again, we abstracted out the vision challenge. We assumed that there's a vision model which can perform a planar decomposition of a room. And then we took each of these planes and traced all of the specular paths from the sound source to the microphone, which in order to trace all of these paths up to n reflections only takes a few seconds for maybe even up to like 30 reflections. So again, we usually try to come up with some kind of interpretable parametric model we can for using a differentiable kind of analysis by synthesis framework. In this case, we came up with an interpretable parametric model for the speaker directivity. Note that this is frequency dependent. Lower frequencies tend to be less directive than higher frequencies. So we needed to have kind of a directivity model for different bands of frequencies. And here we show like the center frequencies of each of these bands and some example directivities. We also modeled the reflection amplitudes of each wall. Again, this is frequency dependent as well. And so for each wall, we essentially had a vector of 32 center frequencies of different frequency bands and modeled the amplitude of the reflection of that specific wall or surface. We put these two differentiable models into our path tracing framework and use this for an analysis by synthesis process where we essentially model the speaker directivity as well as the frequency responses and estimate a room impulse response that should ensue from those different parametric models. And then we continue to update our parameters according to a loss compared to the ground truth impulse response we measured. And by taking these 12 different ground truth impulse responses we had from the different microphones, we can adjust our estimates of each of these parameters in this joint optimization process. Now, at the end of the analysis by synthesis process, we get these meaningful interpretable parameters of the sound source and surfaces in the room. Note that these directivities and reflection amplitudes I'm showing you were just initialized randomly. However, we can see that the drywall in the classroom is much more is estimated to be much more reflective than the wall in the acoustically dampened room. These values and estimates just completely fell out of the analysis by synthesis process. We had no, we didn't annotate the materials of the room at all. And also the speaker arrived at what we would expect of directivity, that the lower frequencies tend to be less directive than the higher frequencies. Note this may be somewhat useful for people measuring acoustics of rooms or like architectural planning. We also get binauralization for free out of this because we are modeling the directions of each ray of sound rather than just using like a model-free approach, which has no concept of direction, but has to learn a sense of direction. We can take these rays of incoming sounds and their contributions, and we can convolve them with a head-related transfer function to estimate the binauralization of the audio, or how would the sound of this source sound differently in the right ear versus the left ear. We can also retroactively change the pose of the sound source or the scale of the room, or even add obstacles within our simulation after we've estimated these salient parameters. So here I'll play a qualitative example of how this can play out. This is in this very reverberant hallway. Initially, I'll play the dry clip, or what you would hear if you were listening to this music on like an MP3 player in your headphones or something. And then I'll play the what you would hear if you were in a virtual version of this hallway as estimated by our model. So here's the initial song.
Sleep, pretty darling, do not cry, and I will sing a lullaby.
So as I play this virtual version of this sound, I'm not sure how much will come across over Zoom in terms of binauralization, but hopefully you should notice a major difference and major shift in the sound as the camera crosses over the virtual speaker in the room. You'll start to hopefully hear the sound coming from behind the listener. So I'm not sure how apparent that was over Zoom. Hopefully it was somewhat apparent. But yeah, basically, yeah, all we needed was 12 microphone positions in this room, and we essentially have a virtual version of this room, which could be used in VR or AR applications from the simple scan of 12 different locations of room impulse response. So with that, I'll kind of conclude this talk by talking about a few different observations we've noticed along the way of all of these works. Especially as I kind of approach these works from a robotics standpoint. First of all, I think audio perception is very important for detecting and characterizing anomalies or also contacts. In terms of the contacts are kind of somewhat difficult to characterize and diagnose purely from vision since they're so minute and nuanced. It also is great at characterizing the unseen. Now, the unseen can be unseen for a few different reasons. One can be occlusions, whereas light doesn't necessarily travel through occluding objects. We have diffraction for audio, which allows us to still hear things despite occlusions that would be kind of the end of the story for perceiving things through vision. It also is helpful for characterizing internal structures, which are similarly occluded. Like it can determine if something, if an object is full or empty, or if there's something broken inside an object. It also is able to characterize microscopic events or structures. Again, as I talk about contact, like very minute or microscopic differences in like the texture of an object can significantly affect the sound, but they may not be apparent through vision. Similarly, I can think of when I'm like taking plates out of my cabinet, if I'm putting plates down, often if I put a plate down and it sounds different than the other plates, that tells me that there's probably like a micro crack in the plate that I need to be wary of and make sure not to heat it in the oven or anything. It also gives us insight into what's happening outside of the field of view. As I showed in one of the motivating videos at the beginning, we had this robot that was attending to what was happening on the table in front of it, but if something drops at its feet, it is not going to be aware of that from vision, but it can be aware of that from audio. However, audio perception has not caught up to vision in a few key aspects. One, simulation is not there. Vision simulation has been very important for the vision community, especially for robotics. And the now kind of photorealistic simulations we have for vision enable new approaches for robotics, but we don't really have anything like that for audio. There also aren't great data sets and benchmarks for audio like there are for vision. There's not even great metrics for those things, as I discussed. And then there's not like go-to models. There are a few different, in the vision community, we kind of have like a canonical list of models we would use for different applications where for audio, we're somewhat converging to some models that seem to work well for most tasks. However, even within those models, there's different design choices you have to make depending on the application, such as what sample frequency should the audio be at? Should it be stereo or mono? What should the length of the signal be? whereas this is problems you don't necessarily have to deal with, at least directly in vision. And then not even the hardware is quite there yet either. There's really great microphones out there, but they tend to be rather expensive and also rather bulky. And along with the microphone, you have to have a recording, an audio recording interface that the microphone, at least for these high-end microphones, that the microphone plugs into. And so there's not really great hardware out there that's both robust to especially for robotics, to being damaged during manipulation, and then also is very compact and could fit in like an end effector or something like that. There are some, as I said, smaller microphones, but even what they plug into is often at the scale of like kind of a semi rack mounted device or something. So if we can shrink those things down and make them stronger, that could be very helpful for downstream applications in robotics. So those are my main observations. And with that, I'd like to thank, as I'm presenting the work of a lot of different collaborators here and have had some really great sponsors that have enabled some of these, the budgets that we did have for collecting these data sets and performing these experiments at a high fidelity. So yeah, thank you.
All right. Thanks, Samuel. That was a really great talk. A lot of stuff. Any questions?
Hello, Gordon.
Yes, Mohsin, please go ahead.
Yes, I was interrupted, so I didn't follow at some points. But when you showed the room simulation and the reflection of the sound in the walls, so you are under the assumption that the room is in a vacuum, or?
No, sorry, could you define on, do you mean like literally a vacuum? Like there's
Well, because I
the
think
room is
I'm not sure if
evacuated
that,
or?
yeah, not sure if that makes sense. But I'm thinking, is there any interaction with air? If there is airflow, strong airflow in the room, will that
Oh,
change?
okay, yeah, I see what you're saying. Yeah, we unfortunately we assumed that air was more or less stagnant, but we did model the attenuation of the sound through the air. I think we did have to use, I believe we had to use some, yeah, that was specifically modeled, but again, the air was considered to be
Well,
stagnant, so we didn't
stagnant.
model the strong airflow.
So you think there is would it be useful to consider also dynamics? Would that change the sound in a way that is noticeable for you, or it's negligible?
Yes, it actually would. I think we're probably, I think this is often most apparent outside because that's when we're most experiencing the dynamics of air, but you may notice that um, sound travels differently, kind of travels with the wind as well. So I suppose if there were an environment, there are a lot of especially factory environments that do have a lot of air moving. And so, yeah, that would be another thing to add to this model now that you mention it, to effectively model how the sound would travel through these air currents.
Okay, thank you. Thanks for a nice talk.
Thanks. Okay, Chris?
Can you hear me, Samuel?
Yeah, I can hear you.
Awesome. Thanks for sharing your work. Hearing anything out of your paper was particularly interesting to me. My background is also in room acoustics and and acoustic simulation and stuff like that. So this definitely piqued my interest. I was curious, so I wanted to clarify something. So when you're computing these RIRs, you're just updating the surface parameters and the source activity, right? Other than that, like the sort of synthesis of the RIR is all based on this either image or array-based method. I'm not really sure what you're using here.
Right, right. I guess it depends on, yeah, when you say image-based method, I guess there's like an interesting overloading of terms that happens between the audio and the vision community. So like we kind of use some vision language and mix that with some audio language, so that might be a little confusing. We essentially were using what in the audio community is called the image source method, to kind of model the reflection about different planes and stuff. So yeah, to answer your underlying question though, basically we needed to pre-compute all of these specular paths and essentially get their time delay of their delay of arrival to the contribution of the RAR as well as their attenuation. So that was locked in at the beginning by this path tracing process. And then after we have the delay of arrival, the attenuation, and the sequence of planes that it strikes, then during the analysis by synthesis, all we're adjusting is the frequency filters of each of those planes, as well as the directivity of the speaker. So the path tracing is pre-computed and fixed, and then thereafter we adjust the parameters. Does that make sense?
Yeah, so would it be inaccurate to say that this is a differentiable image source method of sort of estimating these parameters?
Yeah. I think the image source method is used to kind of estimate their delay of arrival and contribution. So yeah, it is like an image source method, and then using the differentiable part comes into the like frequency characteristics from there. But yes.
Okay, cool. And then a quick follow-up. You mentioned earlier how you get the normalization for free since you get all the sort of DOAs of all the incoming sound sources or the sound rays, right? Was that at all like used in your evaluations? Because from my understanding, you're sort of using these 1D reconstruction metrics for estimating how accurate you're reconstructing RAR. I'm curious if you thought about, all the spatial information that you're sort of, as far as I can tell, not using, and whether or not that was sort of considered.
Yeah, that's a really great question. That gets back to I alluded earlier to a problem that your question kind of reveals, and that is there are not really very good perceptual metrics that are publicly available for this. For binauralization, we did actually do some metrics for comparing ourselves to baselines. Again, some baselines don't even model binauralization at all, but there were some kind of really low level comparisons we could do. For example, the interaural volume difference, like how loud is the sound in one ear versus the other, is one metric that you can compare different results on. But that was not capturing, like if I played some of qualitative examples of audio that both is decently faithful to a spectrogram and also has relatively close interaural differences, that really doesn't capture the nuances of what you're hearing through binauralization. We did find some work that looked really impressive on some perceptual losses that do use binaural audio for their perceptual loss. But again, these were not publicly released. So unfortunately, we weren't able to use them to compare our model. But we do have some comparisons of binaural audio to baselines in our paper.
Yeah, that exact project is something I'm working on here right now. We just released some of that at St. Conference, and it will be shared in the NERVS workshop. So I'd love to chat about that with you more, but I'll let
the perceptual metric now.
Yeah, using perceptual metrics for reconstruction, the reconstruction task using neural acoustic fields. So very similar to what we're discussing. So yeah, let's talk about that another time.
Okay.
I think Francois has a question.
Thanks for the presentation. I mean, I'm not trying to be confrontational, but when I listened to your examples when the paper came out, and and like you say, it's really difficult to just measure. I guess they don't, and they're probably better than anything that's out there, but to my ears, at least, it feels like we're quite far from, I don't know, that it doesn't really sound like what my eyes are saying the space should sound like, or the speaker, it gets some qualitative things correct, going from the front and the back of the speaker, but kind of in what at least feels to my ear like a pretty caricatural way.
You're talking about hearing anything anywhere, right?
Yeah. Sorry.
Okay. Yeah.
Yeah. Since we're looking at, sorry, since we're looking at it, I forgot to mention that. I'm
Mhm.
you know, like, and the videos you put, you only put the results of your thing. So I guess I don't necessarily have this, you know, maybe I'm wrong about what it should sound like, but it's
Mhm.
just, is there, since maybe I imagine you've listened to all of the things, kind of, do you get a sense like, what's your estimation of the qualitative distance with real audio?
Yeah,
And
I think you're definitely right. There is we're not there. I wouldn't claim that at all. I guess our goal in this project was as an academic team, we wanted to like convey a message that hopefully other teams can kind of take and explore more rigorously than we did. As I show here, we're only modeling specular reflections, whereas diffuse reflections are also an important part of the room's impulse response. A question earlier asked about airflow. So yeah, we wanted to convey this message of that these kind of physics-based models and a differentiable framework could be used to get interpretable parameters of the room such that we could, again, like as I listed before, we could retroactively change a few things and have this virtualized version of the room because of these acoustic parameters we'd measured that we could modify if we wanted to. However, if we were to go about this, if I were to kind of try to go further in realism, I would take a rather different approach. First of all, these ray tracing or path tracing based frameworks don't model the interference effects of the waves coming from as they travel through the room and interfere with each other. In order to do that effectively, you need a wave-based solver. Now, that would have been a lot more engineering effort. I hope that the message that this paper shows that there's promise for hopefully making maybe a differentiable wave solver, which can model these more nuanced effects of the acoustics of the room. And thereafter, we can have even more accurate estimates and more accurate models, and hopefully still have some of the advantages that we find from this kind of differentiable parametric model.
Right, just about what you're saying, because the thing is that your data set does have the diffraction and everything, and so your model necessarily tries to compensate for that. So then, in that extent, like, does that impair the interpretability of your coefficients? They're interpretable only to the extent that your model is good. Otherwise, we're trying to absorb something else, what's missing in the model, and potentially get distorted. Isn't that
Yes,
something that could be
that is
happening?
very fair. Yeah, they will have to pick up some slack. Yeah, you're right. The parameters will have to pick up some slack in some kind of in some of the areas that the model doesn't necessarily model very well, some of the confounding variables. So yes, you are right that, and I will say that I wouldn't consider these results are, I would not take these like reflection amplitudes to the bank. I think they show some general trends, but I would be a little surprised if this specific frequency on like the classroom wall, like that this specific frequency was actually reflecting significantly better than this other frequency, especially on the classroom floor, that these like low frequencies aren't reflecting at all. So yeah, I think this is further evidence of exactly what you're saying, of that these parameters do have to pick up some slack in the model, and that for that they suffer in their accuracy. But we are seeing some general trends that suggest that these can be inferred from just a minimal amount of viewpoints, or I guess acoustic points, and room impulse responses, and kind of reasoning about these delays of arrival.
Makes sense. Thanks. Thanks again for the presentation.
Okay.
Can I ask a question?
Please, Yoshi,
Yeah.
go ahead.
Yeah, thank you. Please go back to the page 56. So I want to discuss about the model.
Discuss I'm sorry.
Discuss about the model itself.
Okay, yes.
So the path trace, the path and so in the page 56, I think the model or the reflection is only modeled in the magnitude response, I think.
The what response?
The magnitude response.
Okay.
So you apply the minimum phase reconstruction to obtain the impulse response in the time domain. So how much the waveform itself is accurate with respect to the recorded original data?
Okay, so let's see, you said we're modeling the impulse response in the time domain, and then what was accurate with respect to the real RIO?
Yeah, so yeah, I think that you apply the minimum phase reconstruction, right?
Oh, yes.
So how much it is accurate in the time domain? I think your approach can accurately approximate the magnitude response of the RIO, but I want to know how much it is accurate in the time domain.
Yeah. So unfortunately, we didn't take. I guess we didn't examine the data at high enough of a resolution. We based the minimum phase assumption was we wanted all of our all of the frequency filters for each of the walls to be causal. So we didn't want the frequency filter to start filtering the sound before it even arrived to the wall, which again, there's not necessarily great. We didn't find too many measurements out there which backed up the efficacy of that model for modeling reflections. So yeah, I guess we would have to look at a finer granularity of the time domain, or maybe even the frequency domain, especially the phase, to the extent that the phase is not too influenced by noise, in order to determine whether we could have modeled the reflection in a better model than the minimum phase frequency filter.
In this slide, this shows only one lay. But you will add the whole potential lay light.
One particular it shows only one particular what? Oh, right. Yeah. Sorry. Sorry. Yeah, I see what you're saying. Yeah. So this shows one particular ray and the sequence of surfaces it bounces off, and this one particular ray.
You apply to the minimum phase transform to each lay, like
yes.
Or
yes.
Okay. So you at least model the time delay, but during the travel of each lay, but still the minimum phase is not optimal. Maybe I don't know what model is accurate.
I see. Yeah. What would you say that there's like? Are you aware of a model that, or sorry, like I guess a model other than minimum phase, which would be more accurate that's out there, or would you say that that needs to be measured empirically?
I mean, just how much this minimum phase is optimal for this modeling.
Yeah. Okay. Yeah, unfortunately, we only had kind of our, I guess, our kind of hypothesis to work off of, that was like the most effective way to make a kind of a causal frequency filter. But yeah, we didn't verify that was the optimal model empirically.
I see. Because we are working on neural field for HLDF, and in that field, minimum phase is almost ideal for the scenario. But I'm not sure about in the room impulse response and with multiple reflections. But anyway, thanks so much.
Yeah. Okay. Thank you.
If there are no more questions, can I ask maybe just one quick follow-up to the airflow question?
Yeah.
But much simpler. Does your model account for like temperature and humidity of the room at all, which I know impacts speed of sound?
Yeah, I believe we had to we tried a few different things for that. We tried to see how far we could get without having direct knowledge of some different things. And unfortunately, it was kind of a trade-off between providing more unknowns for our model to optimize for and also giving it a little bit more freedom. For example, if we this speaker has sorry, it's a little bit of a tangent, but like this speaker is considered a sound source, and it's not clear, especially since it has a tweeter and a woofer, like what exactly is the position of that sound source in the room. We were kind of going with the center point, but we also tried kind of letting the optimization adjust the position somewhat. I believe we also tried, if I remember correctly, we also tried letting it adjust the speed of sound slightly as well. And I can't remember if that improved things or not. But I seem to remember that we did try that, and it didn't. Whatever it was, I wish I could tell you off the top of my head whether it did significantly improve predictions or not. But yeah, unfortunately, I can't remember whether we ended up getting rid of that model in our kind of trial and error process to make as faithful of IRs as possible. But I believe that there was a minor gain, if I remember correctly, from allowing the optimization to adjust the speed of sound a little bit.
Okay. Thanks. Okay, any last questions? If not, let's thank Samuel one last time.